When we think about the rise of modern AI, we often imagine this long, slow build over decades. But what if I told you that the foundation for all of it was really ignited by a single pivotal event? Today, we're diving into the story of a two-day meeting back in 1956 that truly changed everything. So picture this, it's September 10th and 11th, 1956. A small group of thinkers gather at MIT for the Symposium on Information Theory. And their goal was, well, incredibly audacious. They wanted to tear down this idea that the mind was some unknowable mystery and prove that it could be understood, measured, and maybe, just maybe, even replicated. And this brings us to the central, almost heretical question they were asking. For decades, the entire field of psychology had been dominated by a single, powerful idea that made this question pretty much impossible to even consider. So before 1956, the world was all about behaviorism. As you can see on the left, it basically treated the mind like a black box. You could study what went in and what came out, but what happened inside, totally off limits. The new idea, the one that sparked a revolution, is what you see on the right, that the mind isn't a mystery at all. It's an information processor, a system, whose internal logic we could finally start to map. And just like that, the field of cognitive science was born. This whole revolution was really built on three conceptual pillars, and each one was presented by a different thinker at that very same symposium. Together, they would basically create a blueprint for intelligence itself. All right, our first pillar comes from a psychologist named George Miller, and he wanted to do something nobody had really done before, actually measure the absolute processing limits of the human mind. He started treating the brain like a communication channel, trying to find its maximum bandwidth. So what did he find? Well, Miller dug through countless studies and started noticing this bizarrely consistent pattern. It turns out our short-term memory isn't infinite. It's limited to right around 7 items, give or take 2. But the really fascinating part isn't the limit itself, it's the clever trick our minds use to get around it. He gave it a name, chunking, and it's basically the brain's own genius data compression strategy. See, instead of remembering every single little bit of information, we group them into larger, meaningful chunks. We don't have to expand our memory, we just pack the information a whole lot smarter. Just look at the example here. When you see that long string of numbers, you don't see 12 random digits, right? No way. Your brain instantly recognizes patterns and groups them into 3 meaningful chunks. The years 1956, 1928, and 1920. You've just compressed 12 items into 3, fitting them perfectly within that 7 ± 2 limit. This one insight is absolutely fundamental to how we design everything from phone numbers to websites today. Okay, let's move on to our second pillar. If Miller measured the mind's hardware limits, then linguist Noam Chomsky came along to define the structure of its software, specifically its operating system, language. Chomsky basically walked in and delivered a knockout blow to behaviorism. He argued that a child simply doesn't hear enough language, enough examples, to learn all its incredibly complex rules from scratch. For him, the only possible explanation was that the basic rules of grammar must be innate, hardwired into our brains from birth. And he didn't stop there. He went on to prove mathematically that language isn't just a list of phrases we've memorized, it's a true computational system. And at its heart is this concept called recursion, the ability for a rule to refer back to itself. Think of it like those Russian nesting dolls. You can put a phrase inside another, and so on, generating infinite creativity from a finite set of rules. And the impact of this was, well, it was massive. Chomsky's work led directly to what you're looking at right here, the Chomsky hierarchy. This way of classifying formal languages became the foundational framework for modern computer science. I mean, the very syntax of the programming languages we all use today, it's built on these principles. Okay, so let's recap. We have a mind with a limited capacity and a built-in grammar. Our final pillar provided the shocking proof of concept. This was a demonstration by 2 guys, Alan Newell and Herbert Simon, that a machine could actually replicate human reasoning. And they called it the logic theorist. It was, for all intents and purposes, the world's very first artificial intelligence program. Just a few weeks before the symposium, it successfully proved a theorem from this famous, dense mathematical text called Principia Mathematica. And by the time they presented, it had already proven 38 theorems. It even found a more elegant proof for one than the original human authors had. But here's the crucial part. It wasn't just what it did, but how it did it. Instead of just brute forcing every single possibility, it used something called heuristic search, basically using rules of thumb and educated guesses to explore only the most promising paths. It was designed to think less like a dumb calculator and more like an intuitive human mathematician. And that idea became a cornerstone of AI. The impact was immediate. Even Bertrand Russell, the guy who co-wrote the book, was just astonished. The idea that this mysterious, creative act of mathematical proof could be broken down into a set of instructions for a machine, that was a complete revelation. So these three pillars, they didn't just stand on their own. They fused together to create this unified blueprint for intelligence. Which brings us to the big question. Where has that blueprint taken us, 70 years down the line? What that 1956 symposium really gave us was this incredible synthesis you can see laid out here. Miller showed us that capacity is limited, which means we need efficient chunks. Chomsky revealed the computational structure of those chunks and language, and then Newell and Simon proved that reasoning itself could be modeled as a kind of intelligent search. For the very first time, the mind was officially reframed as an information processing system. And you can draw a perfectly straight line from that moment all the way to today. The symbolic, rule-based AI of 1956 has evolved into the probabilistic, agentic AI we have now. We've gone from systems that prove static theorems to systems that can tackle complex, open-ended problems using things like persistent memory. And yet, and this is a big and yet, for all of our incredible progress, a core challenge is still staring us right in the face. Today's AI is phenomenal at pattern recognition, but it still really struggles with genuine, fluid, abstract reasoning, the ability to combine known ideas in totally new ways. Some researchers call this the compositional cliff. This chart just lays the gap bare. The ARC-AGI benchmark is designed to test this exact skill, learning a core principle from just a few examples and then applying it to a brand new puzzle. And as you can see, humans solve these with near perfect accuracy, but our most advanced AI models, they're scoring below 1%. They just can't make that intuitive, abstract leap. Which all brings us to our final question. The symposium in 1956 gave us an undeniable blueprint for building machines that look like they're thinking, but did it give us the blueprint for intelligence itself, or just a much more sophisticated way to build mimics? The answer to that is probably going to define the next 70 years of AI.